Taylor polynomials give us a way to model more complicated functions using polynomials. Now the reason we want to do that is because a polynomial is generally pretty easy to deal with. We've dealt with polynomials for a really long time. They're easy to take the derivatives of, they're easy to integrate, so there's a lot of good properties to polynomials that we would like to use here. So the idea, let's say that we have some function here, I don't know, here's our function, f of x, and I want to approximate it using some polynomial. Now here we're assuming f of x is not a polynomial. I mean, it could be, but generally we are assuming it's not. Now, I do generally would like to approximate the entire function, but just in the word, we're approximating this function, which means generally we're not going to do a good job for the entire thing. So most of the time, there's generally a place that we want or we're concerned about. So let's say that we are really concerned about this function at some value c. Well, we're going to approximate this with some polynomial, and I'm going to call that polynomial p of x. Well, the easiest way, if we just want to approximate the function at c, is just figure out what the y value there is, right, f of c, and it would exactly approximate this. So if we were just doing at one point, we could say p of x is just f of c, right? It's just that y value, right? We say it's 7 or something. Then it would exactly match the function right there. But it would do a really lousy job of matching the function everywhere else. So maybe we can use a higher order polynomial, right? This doesn't have any x's in it at all. So what if we made a line, a linear equation? Well, using a linear equation, we'd still probably want it to have the exact same value there, but wouldn't it make sense if we also matched the derivative there, right? So the slope of the tangent line here is the slope of the curve. Now notice this line approximates the function as long as we're pretty close to c here, right? It gets really close to the function right there. So in that case, we'd have the p of x would be at some c value, and then we'd add on something that has to do with the derivative, right? And this isn't correct, I'm just making stuff up. And then we'd have some power of x because we know that this is a linear term. Now I put x minus c there because remember we want this at c, so you'll kind of see what we mean. Because another way to think about it, when we're at c, we want it just to be this value here, so I need this to go away at c. It's kind of another way to think about it. All right, well this line would do a pretty good job of approximating that polynomial. But what if I wanted to add in another term? Well, what if I said the polynomial I want to approximate this not only has the value there, not only has the slope there, but also has the same concavity? Well, then I could use something, say like a parabola. A parabola that has the exact same slope right there, the exact same concavity, may look like that. Now notice, the parabola would match the curve for a longer distance out there. So the next term, since we're talking about concavity, would have to do with the second derivative, right? And since now, in this case, we're using a parabola or a quadratic, this next piece would be a squared term. Now again, I want that to go away at c because I just want this to have that value at c, so I said to be x minus c. So we could keep doing this idea. Not only do we want it to match the function value, the first derivative, second derivative, what if we also wanted it to match the third derivative and the fourth derivative? So you get the idea. So for the third derivative, we'd have something like a cubic function coming through here that would match, that doesn't work, not only match the concavity, the slope and the value there, so it may come up through here like this and head out like that. So notice, I know it's all kind of blending together, especially on the video here, but you can see that the blue would probably match this farther and farther away. So the idea here, again, so this would be something like this. The third, that's a c, sorry. The third derivative, x minus c to the third, and so on and so forth is kind of the idea. Now this piece here that I've been putting here was just to kind of get an idea of what's happening. This isn't quite right. It's close, believe it or not, but those pieces aren't quite right. Let's see if we can figure out exactly what this needs to be to do a polynomial approximation of a function. All right, so there's the concept. let's see if we can put this concept into practice mathematically. All right, first off, we need to define what a Taylor polynomial actually is. So we're going to call this Pn of x. This is going to be an nth degree polynomial. So P3 of x will be some polynomial, I'm just making something up, x plus 4x squared minus 6x cubed, right? This is a third degree polynomial. Now, notice this is one of the few times when we do the polynomial order backwards. It's actually in ascending order. We normally do descending, but these are always going to be ascending. So that's all P3 means. It means it's a polynomial whose degree is going to be 3. So generically speaking, Pn of x is going to be a0 plus a1. Now, I'm going to assume that this one here is centered at some arbitrary value, so x minus c plus a2 x minus c squared plus all the way out to the very last one, an x minus c to the n. Here we say where c is the center. Now, there's a couple of different ways you can say this. You can say that this polynomial is centered at c, or you can say that it is, sometimes books say that it's expanded around c as well. Now, if we take this and we center it at 0, if it is centered at c equals 0, then it's called a Maclaurin polynomial. Check how you spell Maclaurin there. Sorry, Mr. Maclaurin. I may have spelled your name wrong. It's called a Maclaurin polynomial. And I'm pretty sure I got the A and the U backwards there, I think. All right, so here's the idea. If you hear the word Taylor polynomial and Maclaurin polynomial, they're the exact same thing. The only difference is a Maclaurin is a special case of the Taylor polynomial. It just happens to be centered at 0. Now, since centered at 0 is the one we actually do the most, we actually end up doing more Maclaurin polynomials than Taylor, even though it's still a Taylor polynomial. All right, let's actually come up with this, this polynomial. Now, I need to figure out what these constants are, these a sub n's. Now, when I first wrote this down, since we said we wanted to match I just had the derivatives here in f to the third, just to kind of give you an idea that that was kind of what was going to happen here. So let's do this. Let's say that we want our f of x to be modeled by some Pn of x. So our f of x to be equal to some a0 plus a1. I'm just going to center this at 0 to make it a little bit easier to see. X plus a2 x squared all the way out to a sub n x to the n. Now, the only difference if I didn't center this at 0, everywhere there's an x, we'd have an x minus c. So in this case, I'm going to say that this is going to be 0. Okay, now we decided, remember when I first drew the picture, the easiest approximation would be if we just had the function value matched there. So I need this thing at the center, which I said was 0, to be equal to this side. So if you put 0 in everywhere there's an x, you just get a0. So we actually know what a0 is now, right? Remember, we know what the original function is that we're trying to model. We can evaluate that at 0, so we know what our first term is. We also said that we wanted our derivatives to match. So we want f prime, which would be the derivative of this. Well, the derivative of a constant is 0. So that's a1 plus 2a2x plus, I'm going to do the next one, even though it's not right there. That would be 3a3x squared all the way out to n a sub n x to the n minus 1. Right, this would have been the cubic term right there. Okay, so if we want this to match at the center, we want f prime at 0 to also be equal. Well, if you put 0 in for x again, we get a1. And let's do this a couple more times. The second derivative, well, the derivative of this is going to be 2a2 plus, Now to show a pattern here, I'm going to bring that down and not multiply. That's 2 times 3a3x plus all the way down. This last one's going to be n minus 1 a sub n x to the n minus 2. Now again, we want this to match at the center. I said the center was 0 here. If we plug in 0, everything goes away except for this first term, so we get 2a sub 2. Now this is the first time we have to do a little bit of solving. We should be able to see here that a sub 2 then is equal to the second derivative at 0 all over 2. So far we have our first couple, right? We have a a0, a1, a2. Let's do one more here. So I'm going to squeeze it down here at the bottom. So our third derivative, let's see, that goes away when we take the derivative. So this is just going to be 2 times 3a3 plus so on and forth. And down here, this is going to be n minus 1, n minus 2, a sub n, x to the n minus 3. Now this at 0, same thing happens. Everything after the first term has an x, so it goes away. So this is 2 times 3a3, which implies we can now figure out what a3 is. a3 would be the third derivative at 0 over 2 times 3. So there's our next term. Now if you kind of see what's happening here, each time we take a derivative, we bring down a power, which gives us this type of thing happening here. And if you notice, this is a factorial, right? You multiply every number down till you get to the bottom. Because if we took this derivative n times, we'd have n times n minus 1, n minus 2, all the way down to 2 times 1, and that would be our last term. So our formula for the Taylor coefficients, I'm going to stick it right here. Can be given by this formula. Well, what do we have? Notice here, let's kind of work backwards. Here we have the third derivative at the center over 2 times 3, which that's, if we added a 1 there, which doesn't change anything, that's 3 factorial. Here we have the second derivative at the center over 2, which we could write that as 2 times 1, which is 2 factorial. Here we have a sub 1 is equal to the first derivative, and if you wanted to, let me get that out of the way, we could write that over 1, which would be 1 factorial, and this one gets a little weird. This is the no derivative or 0th derivative, and I can write that as 0 factorial. Remember, 0 factorial is 1. So if I just follow that form, then our Taylor coefficients, every a sub n is the nth derivative evaluated at the center, evaluated at c, all over n factorial, right? Our n was here, and then the denominator is the factorial, so this is n factorial. All right, what we end up with here is a formula to be able to come up with any Taylor polynomial that we want of nth degree using these as the coefficients. All right, let's give this a shot so you can kind of see how you would put this into practice. Let's say we wanted to find, let's say, p sub 4. Let's do p sub 3 for the first one. It's a lot. Let's go p sub 3 for f of x is equal to the natural log of 1 plus x. Okay, so p sub 3, here's the way you need to think about it. We got to get all the pieces before we put it together. P sub 3 for this function means we're going to need a sub 3. A sub 3 has to do with the third derivative. So we might as well go ahead and find all the derivatives. So if f of x is natural log of 1 plus x, f prime of x would be 1 over 1 plus x times 1. F double prime of x, remember you could write this as 1 plus x to the negative 1. That'd be negative 1 over x, 1 plus x, 1 plus x squared. Same idea as we go with the next derivative. The third derivative at x is going to be 2 over 1 plus x to the third. Okay, now we also know that we need to evaluate every one of those derivatives at the center. Now notice in this case, I didn't give us a center. So let's say here that C equals 0. Let's do a Maclaurin polynomial for our first one. Let's make it a little bit easy. So at C equals 0, so I'm going to say now at C equals 0, f of x would be the natural log of 1, which is, f at 0 is the natural log of 1, which is 0. F prime of 0, f prime of 0 is 1 over 1 plus 0, which is 1. F double prime of 0 is negative 1 over 1 plus 0 squared, which is negative 1. F triple prime at 0 is 2 over 1 plus 0 squared, which is 2. Okay, so P3 for this, let's go ahead and write it out. I generally like to expand it out first. So P3 would be A0 plus A1x plus A2x squared plus A3x cubed. Now remember, since it's centered at 0, these are just x's and not x minus c. So what would P3 of x be if we now put in our coefficients? Well, A0, we know A0, here, let me do it like this. We know A0 is the 0th derivative at our center all over 0 factorial. The no derivative just means the function, remember 0th derivative, add there would be 0. So A1 is the first derivative at 0 over 1 factorial. So f prime at 0 is 1 over 1 factorial is 1. A2 then would be f double prime at 0 over 2 factorial. So f double prime at 0 was negative 1 over 2 factorial is 2. And let's put our last one here. A sub 3 would be the third derivative at 0 over 3 factorial. The third derivative at 0 is 2. 3 factorial is 6, so that would be 1/3. Okay, there's all we need. So let's put it in now. We know A0 is 0. I'm going to go ahead and write it there. A1 was 1, so that's 1 times x. A2 was negative 1/2, so let me go and write that as a minus. Negative 1/2 x squared. A3 was 1/3 x cubed. And there we go. There's our third degree Taylor polynomial. So if you approximate this pretty close to 0, this function here in this polynomial should have pretty close to the same value. Now I need you to check this. Grab a calculator real quick, and let's say that I wanted to evaluate this at approximate at x is equal to, let's go really close to 0 and go 0.1. So grab a calculator on your own. I don't have it here for us, but what if I said, what is f of 0.1 and what is p of 3 of 0.1? Take a look at those and see how close they are to each other. Now, they should be really, really close. The problem is, remember, we're saying that this will approximate the function pretty close, but not necessarily really far away. Our center is at 0, so how well do you think this would do if we wanted to approximate it at, say, 5? So then I want you to check P3 at 5. What do those equal? Now, these two, when you do it in your calculator, should be extremely close to each other because we're really close to 0. These two are probably not going to be very, very close at all because we're getting quite a ways away from our center. All right, so there's your Taylor polynomial, or Maclaurin in this case. Let's try one more, maybe a little bit easier, and then we'll talk about how we can tell how bad our approximation is going to be. All right, so let's say that I wanted to find, let's do P4. Let's change our function, make it a little bit easier. Let's go e to the x. However, I am going to change my center. Let's let our center be equal to 1. Now this can give some really ugly coefficients, but let's take a look at it. So I want to approximate this exponential using P4, and I want this thing centered at 1. So for P4, I know I'm going to need the fourth derivative, so go ahead and find four derivatives. That's our function. The good news is, well, it's e to the x, so all of our derivatives are just e to the x. And our fourth derivative is also e to the x. Now we want to evaluate this at x equals 1, right? At our center. So f of 1 is e. F prime of 1 is e. Double prime of 1 is e. Triple prime of 1 is e. And the fourth derivative at 1 is, well, e. Notice I picked an easy one. Okay, so now what we got to do is put together our pieces. So let's find our coefficients real quick. So a naught, remember a naught here is just going to be the 0th derivative at the center over 0 factorial. So that's e over 1, or just e. A1 is the first derivative at 0 over 1 factorial. That's e over 1, which is e. A2 is the second derivative, sorry, that's a 1, at 1 over 2 factorial, that's e over 2. A sub 3 is the third derivative at 1 over 3 factorial, so that's e over 6. And our fourth one down here is the fourth derivative at 1 over 4 factorial, which is e over 24. All right, again, I'm gonna only have a little bit of room here, so I'm gonna squeeze it down here in the bottom. So P4 by definition is gonna be a naught plus a1. Now it's not x here because our center's at 1, so it's x minus 1, a2, x minus 1 squared, a3, x minus 1 to the third, and our last term, a4, will be x minus 1 to the fourth. Now that we know what all of our coefficients are, we stick in our coefficients, and this will be the polynomial that approximates e to the x centered at 1. So our coefficients are e times x minus 1. What was the next one? E over 2. E over 2 x minus 1 squared plus e over 6 x minus 1 cubed plus e over 24 x minus 1 to the fourth. All right, so pretty scary looking, but that will approximate the function. Now you can see not only does it approximate the function around the center, around 1, it's actually at 1 is exactly equal to the function there, right? If we plug 1 into there, we just get e. If you plug 1 into this mess, every term goes away except for the first one, which is e. All right, so we've seen that this will approximate a function close to our center, but how do we know how good the approximation is? Well, that gets a little more complicated. To figure out what the remainder of a Taylor polynomial is, what you actually have to do is look at the next term, because the next term is going to be the pretty much guiding source of all the remainders. Because these things are going up in power, this one right here, the next term is going to be one that really dominates this, because in general these, for this to converge, which we talked about before, has to be getting smaller as we go out. So if we take a look at the next term, our remainder, let's just call it r sub n of x. So our remainder term is based off of the next one. So for the next one, this would be the n plus 1 derivative. So the f of n plus 1 evaluated at some value, we'll talk about that in a second, over not n factorial, but it'll be n plus 1 factorial. And then we have x minus c to the n plus 1. So for each one of these would be x minus c to the n plus 1. Now where do we want to evaluate this at? Well, here's the idea. We're trying to approximate a function some distance away from the center, right? Here's our center, and we're trying to approximate it at some value x. Kind of like here, if I wanted to approximate e of 2, I could plug 2 in here to this polynomial, and it would give me an approximation. Now, there's got to be some value between these two that maximizes that derivative. You find the value that falls between c and x, z falls in between c and x. There's got to be a value there that maximizes it. So that's what this z value here, it's the value that maximizes that derivative between those two values. All right, so a little bit complicated, but it will let you know how close your approximation is going to be to the actual value. All right, Taylor polynomials and Maclaurin polynomials are very useful, but since they don't approximate the function everywhere, they do have some problems. So we're going to take a look at how we can fix that in the future.